Okay, so where are we? Let's run this. Every time, yeah, it's cool. So we have, let's recap that. So we have this word with 1, 2, 3, 4, 5, 6, 7, 8, 9, but it's a D model 10, max length 15. So D model 10, right? So that's the depth in which, so dimension depth for each token representation. And we've got it basically split into two heads. Okay, so that's what we got last time. So tokenize, blah blah blah, and then what are we doing here? That's what we go, and then we do multi-head attention and call XXX. So multi-head attention, multi-head attention, and we basically, this does the initialization of these Q, K, and V things. And then so this is the initialization, and then what the call does is it does the projection, and then it prints them. So we don't care about this anymore, and then we're splitting heads. Okay, so that's what we are now, and now it's about the attention stuff. Okay, so what is it that we're trying to do? So once we have this these split into the heads, right? So now it's where the dot product attention comes in, and this is this thing here, QKV. Okay, mask none. So let's can you explain dot product attention? First of all, how do we even call it? Okay, we just call it with this, right, with the heads. So how do we even call that? Cool. So Ghost Rider, can you explain in detail what is this function doing in the context of the multi-head attention pieces? It is a function that takes queries, keys, and values as inputs and outputs a tensor that combines values according to how similar the queries and the keys are. Okay, so it outputs values. It combines values according to how similar the queries and the keys are. It's applied to the query keys and the values of all being the same tensor is applied with the queries, keys, and values all being the same tensor X after it has been projected to subspaces of the original embedding space by the weight matrices WQ, WK, WV. The output of the dot product attention is concatenated across the heads and multiplied by a final matrix dens. In the dot product attention function itself, we first compute scores by matrix multiplying the queries with the transposed keys. We then normalize the scores before multiplying them with the values to get the final output. Okay, we compute scores by multiplying the queries with the keys, and then the values to get the final output. We can optionally mask the scores to exclude certain values that we do not want to attend to. Okay. So, so we're transposing the keys, multiplying Q and key. This is normalization, I guess. Normalizing. Then the mask. Okay, so that's like a 0 thing. So the mask, we ignore it for now. I don't know what is this used for. The attention weights. NP softmax scores. Why softmax? attention weights. Because it looks like some kind of activation function, right? But here we're multiplying Q and K, and there's no V. Oh no, here, okay, we output this with V. So we multiply this with V. The output and the attention weights. Why do we return two things in the first place? Copy. So the scores tensor contains similarity scores between each word in the input sentence and each other word. Since we want to focus on attention only on a few words at a time, we use the softmax functions to transform these scores into probabilities that sum up to 1, indicating the importance of each word for the current attention step. Okay, so it's just to transform. So this is the normalization, actually. Dot product attention. So let's so why so first of all, why are we transposing, and why okay, so so we're essentially splitting these into two heads. That's fine. Okay, so now we're projecting this into like 3 subspaces, right? And we just look at 2 of these subspaces. I think I said that last time. Why demodel the subspaces? Why this shape? Doesn't matter. It actually gets tricky to follow because high level kind of makes sense. We're doing the projection. I have to remember why D model times D model. So I think I kind of answered that question last time, but I forgot, so I'll probably go back to the video and we'll see. And why are we okay, but I kind of roughly understand what is happening. So we're just basically doing a projection of these. So we have an input matrix, an input tensor that essentially has the words, right? So it has the words encoded. That's cool. Let's just forget about the splitting because it makes things a bit more complicated for now. So let's imagine we just have these. So we have essentially X, right? That's all we call this width. X is essentially our thing. So this is our matrix which has the encodings. Okay, so that's the this kind of things here at the beginning. So it has the encodings for each word in a sentence, and then what this is doing is we're projecting it into 3 subspaces. So essentially we're kind of looking at 3 different. You have to think about this as if you're looking at these kind of high dimensional arrays from 3 different angles in a way, right? But then what we're doing is we're actually comparing. Yeah, so what we're comparing then later on, it's funny because what we're comparing is, if you think about the dot product as being a measure of similarity, right? Because it's like, if you think about, I think it was like if you just think about simple vector space, right? And it's like 2-dimension vectors, if they are, I think, perpendicular, so totally different. The dot product is 1, I think, or 0, I think, and if they are parallel is 1 or something like that. Like this, it's kind of like an easy way to measure. It's a one way to measure how different 2 things are, and it extends to multiple dimensions as well. So, but if we're doing it like this, then what does it mean? So if we're essentially just, what we've done is we've split our words representations into multiple with different projections. What we're comparing is these projections, right? So we're comparing the Q projection with a K projection, and then essentially multiplying it by the V projection. So yes, we're comparing words with themselves, but we're doing it looking at different aspects of them, I guess. That's what feels that's what does not fully click yet to me. It's why are we comparing different projections, right? So maybe it goes right again. So okay, so if I understand this well, we are comparing different projections of the same input, right? Why do we do it this way instead of comparing directly the higher dimensional input? So compare different projections of the same input in multi-head fashion. The reason for this is that multi-head attention organism learns different relationships between the input vectors by attending to different parts of the projected input in different subspaces. This allows the model to capture more complex and nonlinear relationships between the input vectors than if the model were just trying to learn a single weight matrix. By projecting the input into num-head subspaces, that's wrong. So we can think of each head learning a different submanifold of the input space that is better suited to the task at hand. The final multi-head attention output is then concatenated to the outputs from each of these submanifolds that are optimized to capture different types of dependencies across the input vector spaces. So the fact that we're doing the transpose, I think this is just a technicality. That's how you do it. That's what the dot product is. The generalized dot product is you I think you transpose one of those. That's fine. But essentially it's like saying, you know what would be cool? Because I know I'm working on well, we could have like a whiteboard extension. I should probably work on this, like a whiteboard extension, something like Paint Online or something like that. Like I think that should be easy, right? Because I think you can just integrate like a canvas, like an HTML canvas or something like that. So essentially, it is nothing like this, right? If I look at the extension store, not here, but extensions, where are extensions? I don't think there's anything. Hex editor, no, that could be a quick win. Anyway, so essentially, if I think about, I'm trying to understand if that makes sense. I'll probably stop here. So let's say I have these vector in 2D, okay? And I'm taking this projection, so sort of the actual you know, x and y projections. So let's say I'm taking these two, although that's a special case, and I don't want to, yeah, maybe that's not going to work out well, you know. So I'm kind of like, we've taken, so this is y, sorry, this is x projection, right, of these. And then essentially what we're doing is we're comparing these two. So we're comparing x and y. That's interesting because it kind of makes sense in a way. Yes and no, because I thought we were comparing in between words. That's what I'm not getting in here. It's like, where are we comparing between words? Okay, because the attention weights, so this is this, okay, maybe this is what we're doing by doing the transpose, right? Yeah, I think that's what we're doing by doing the transpose. Actually, that's why we're doing the transpose, because let's say I have, here's like token 1, token 2, token 3, right? Let's imagine I have, so these are of course arrays, right? But whatever, like this is my tensor. So if I do the dot product of the transpose, would then be T1, T2, T3. So essentially the result of these, right, is a matrix where we're kind of doing these times these, plus this times this, plus this times this. So we're actually comparing here maybe we're doing it the other way around then. Yeah. If this is a row and then this is a column, then we're doing essentially no, that's fine, whatever. I think so, because here we're just basically comparing each other. Because if you wouldn't transpose it, then you would do this one. Yeah, then you would be adding these things, exactly. So if you're doing like that, then it's like so first row with first column. So this is just essentially T1 with T1 itself. Then first row with second column, so it's T1 times T2 and T1 times T3. So you're comparing all these, and then you're doing T2, T1, T1, T1. So you're building. I think that's what happens, right? Can you give me example of a row times call matrix multiplication? So you're doing the column, this and that, yeah. So you end up exactly. So you end up with like 2 by 2, yeah. So these times these, then these times these, exactly. That's correct. So this is why you're comparing the words with each other. Okay, so that kind of makes sense. Yes, that's why you're doing a transpose. Otherwise, you wouldn't be comparing the words with each other. But again, they are just the kind of different projections. Okay, so I think the idea is you're projecting stuff and then you're comparing different projections. So in a way, this is just, you know, kind of a way to say maybe part of the meaning of this word is related to part of the meaning of that other word. You know what I mean? It's quite a strange thing, but it's crazy that it actually works. It's if you think about it, it's quite mind-blowing, right? So you're essentially doing you're projecting it into 3 subspaces, then you're comparing 2 subspaces and multiplying. What's the point of multiplying by v though? What's the point of by the V matrix of the N. Function. So along the time axis. Multiplying the attention weights by the value matrix is the final output vector which of the input word or sentence. So the scale after computing attention weights. First of all, why are we even returning? So why is so the attention weights are calculated. Okay, so the attention weights are between these two things, yes, and then the so why is this returning two values? Why is so the purpose is to calculate the weight of the weighted sum of values. Weighted sum of V as attention scores, which are first scaled by the square root of the dimensionality of the queries, normalizing softmax. So the attention weights contain the attention weights themselves, but then show how much each input word contributes to the output vector. Okay. Matches with the query. The word we are currently encoding. In summary, the output tensor. So we take the attention weights. Essentially, we're multiplying the attention weights to V itself. V is yet another projection, right? But V is yet another projection of our original X. So what's the interpretation of multiplying the weights there? But it has a different set of learned weights than Q and K. The purpose of V is to contain all the information from the input tensor that may be relevant to computing attention scores for any query, to condense the input representation more informative in compact form. During the attention computation, the Q and K matrices allow us to compute the dot product. Okay, this is similar to attention scores. So then normalized, yeah. Finally, we're computing the weighted sum of the V tensor with the attention scores, with scale attention scores. Okay, but this is it. Allows the attention mechanism to extract the most relevant information. Okay, so we're essentially taking three subspaces. So we're using two of them to calculate the relationships, sort of what we think the attention should be. And then we're applying this attention to that subspace V to basically just say, you're applying what you've learned, you're applying the attention weights to another projection that that's the one you're going to be working with, I guess. Couldn't you apply the weights directly to X instead of V? Interesting. Okay, that's exactly that, by using the potential itself as the V matrix. Interesting. However, in practice, it's often useful to project. Look, we're learning something new. That's cool. Okay, so yeah, that's how it was done. So you take the weights, and that's because that seems to make more sense to me, right? So you apply them to the input vector. But yeah, the idea here is you project it, so you kind of do something else, I guess, right? You learn something else, just rather than, I don't know. I'm not so sure that makes sense to me though. More expressive power, enabling the model to track different aspects of the inputs that may contribute differently to the output. Yeah, but if you're not doing that, you're not. If you're using V, you're not using X. Does it matter what you're using? You know what I mean? Like, what if your projection is just super bad? Because it starts randomly, right? So what if your projection is super bad? Unless part of the training process somehow is to kind of keep repeating these, and so you're doing multiple projections, and so you're kind of learning an average out of that. Maybe. The projection of the input tensor into a separate V tensor can enhance the model's interpretability, as it allows us to visualize the attention weights applied to the input sequence and better understand what parts of the input are contributing to most of the output. That's not true. It just makes it worse from an interpretability perspective, because you're just working on another subspace. You're just projecting stuff. Anyway, but the high level steps are, and I'm assuming that's not going to work if I hit run. Why is it complaining about? What is this? Empty tuple. I think that's just gonna break, but that's because debug. To the call method. What? Scale. What? Okay, so 2. So what is the difference between these? What? Unexpected indent? What the hell? Oh, okay, there's something odd in the way this is called. Okay, but that's a technicality. I think I just have to fix it in the next video. But I think okay, so we haven't run this, but it's been 30 minutes of like at least theorizing about that. So what is happening here is, and if we ignore for a second the multi-head stuff, we are doing a so it's calculating. You do the dot product attention. I think we'll just separate that into the function. So you're doing these essentially to calculate the attention weights between the Q and K, and then normalizing it, and then essentially applying the weights. You could do that to X, but you do that to values. My thinking is the way the training is going to look like later is, because of the random initialization of these, you might actually in multiple runs maybe learn an average of these, and then we'll return these two things. So cool. And then once we have these two things, what are we doing with them? Scaled attention. You concatenate the attention. That's the output actually. Scale attention weights and attention. And then we do these dents. I don't know what is these dents though. What is the purpose of dents? To project the concatenated attention weights back into the original model dimensionality after concatenating the attention weights across all the heads. Okay. A dense layer represented by sub-dense, which projects it back into the original model dimensionality of batch size, max length B model. This dense is calculated here, right? Here, dense. But that's not true because it's D model. So something's off. Shouldn't these have different shape? And then okay. So it's a way to recombine. It's a way to recombine things by multiplying. I guess. So which of these elements are learnable? So which of all these pieces are the ones we fine-tune to learn stuff? I think it's just. Yeah, I was gonna say. The trainable parameters that get fine-tuned during training are the weight matrices. Yeah. Q, K, V, and dense. Exactly. During training, the model learns to update these weight matrices to minimize some loss function. Exactly. To make better predictions. By minimizing the loss function, the model gradually improves in its ability to perform the target task. Okay, so essentially, yes, that makes sense. Of course, you vary that. Yeah. So essentially, this is what it's allowing to. It's basically because you're moving the way you're adapting these matrices, then you're adapting the things you're projecting. So you're learning to basically project it to the subspaces that tell the most information about the relationships. And then this is just yet another. Could you just keep self-dense altogether? In theory, yes. That was my thought. I mean, yeah, it's like it's like let's just put a little bit of salt here, a little bit of pepper there, and then we're just gonna cook into some nice stew. Anyway, cool. I think I understand then how this all goes. I just need to fix that code. I understand what the logic is between this kind of recombination stuff. This idea, right, of the subspaces and whatnot. Yeah, and then we just clean up the code and get it to run. And once it runs, then we can go to the next step. Essentially, I guess the next step would be the feed forward. Because this is I guess you need the whole set of boxes to do the training actually, because you have the input and the output. The output is in the training, right? So and then you basically are learning the relationships between all the input and the output that you have. But that happens up here. I don't know why you're doing mask multi-attention in here, what the point of these is. But then you're kind of combining these, what you've learned in here, together up here. And then you're kind of, you're kind of done. Okay. But the softmax is here. I guess softmax can also be in here, I guess. I think we've done these. So the feed forward parts. Yeah. Okay, that's for the next session. I think we're good for this one. I know it's been just quite theoretic. There's not been any coding, but it's like just to understand what these lines are supposed to do. So we just need to get it. We just need to get it right, so it works. I don't understand why this error is here. See you next session.